So welcome back to part 2 of the video explaining the main points of chapter 13. In this video, I'll discuss the 3 types of tests that we're going to conduct in this chapter, as well as the 2 ways we can calculate confidence intervals. So the first test, and probably the most important and most tested test, is the test for the significance of the slope. So please pay attention to this one. Once you have a regression equation, it is important to test for the significance of the slope. If the slope turns out to be nothing or insignificant or not different than 0, that means the line or the relationship between x and y is flat. So there's no point of the regression equation. However, if the test proves that the slope is significantly different than 0, either positive or negative, that means a relationship exists, and therefore the model is useful or practical. So we'd like to test for the significance of the slope. Step 1 is always to write the hypothesis, and you always test for the population parameter. So this is a side note, just in case this happens on the exam. This could be a trick question. If one of the options was this is incorrect. So we never test for the sample or point estimate. We always look at the population parameter, which is written in capital Greek letters, big beta. So step 1 is your hypothesis. Step 2 is always to calculate or determine a critical value. The critical value will be either a z or a t, depending on if you have a large sample size or if the population standard deviation of beta is given to you. And if not, then you use t. T is going to be based on obviously alpha. In this case, because it's equal to and not equal to, it's going to be a two-tailed test, so alpha divided by 2, and it's going to be based on n minus k minus 1 degrees of freedom. K is the number of variables used to predict y. In a simple linear regression, it's going to be 1, so the entire degrees of freedom are going to be n minus 2 degrees, which is often what is written or what you see in your textbook. Step 3 is to actually conduct the test. The test is quite simple. It's simply a comparison between what you observed from the sample versus what you predicted, divided by the standard error of the beta term. This is very much the same as what you've seen before. Observed, expectation, standard error. The standard error in this case is the standard error, the standard deviation of beta. So if beta had a distribution, this is big beta 1, it has a standard deviation as well. This is the standard deviation of that distribution. Calculating the standard deviation of beta, or in this case beta 1, is a little bit tedious because it involves several equations. I wrote them out for you here. This is leading into this. This is the standard deviation of the error terms. It comes from this equation. It's the square root of the variance. The variance comes from this equation. MSE stands for mean sum of squares. The error. And it is simply the sum of squares of the error divided by its degrees of freedom, n minus k minus 1. My suspicion is you will not be asked to calculate this, but it could happen, and it has happened before. One extension of the testing for the significance of the slope is that you are then able to calculate the confidence interval for the regression slope. So between what upper and lower limit does the real big beta or beta 1 occur, and at what level of significance. So essentially, just like always, you start off with your point estimate and you add and subtract to it a margin of error. The margin of error is going to have your critical value, and it's going to have your standard error of the term right there. So since you already have it from your testing, this should never be a very difficult exercise to finish. So essentially, you're going to create a confidence interval, an upper limit and a lower limit. This is your point estimate right here. And you're saying that within some level of confidence, you are sure that the real population parameter is somewhere in between those upper and lower limits. Next, what you can do is you can test for the significance of the model, or when it's simple linear regression, it's the test for R squared. So is R squared significant? So as always, we start off with a hypothesis. We're going to set up our hypothesis like this. It's going to equal to 0 or greater than 0, obviously because rho can never be less than 0. And essentially, the test is going to be a ratio between SSR over its degrees of freedom and SSE over its degrees of freedom. And for those of you who have been following with me, this is just MSE and this is MSR. When you choose your critical value, which is step 2, you choose based on n minus k degrees of freedom. So we're going to see a problem and we're going to look at how this critical value is chosen. We choose it from the F table, a distribution that's a little bit different than what we've seen before. If your F observed or your F star is greater than your F critical, therefore you reject HO and you conclude that the model is significant. Lastly, you can test for the significance of rho itself, so the correlation coefficient, since it's a value between 1 and -1, with 1 and -1 being perfect linear relationships. Anything that is around 0 or 0 is no relationship. So we'd like to make sure we test that point. So we're going to set our hypothesis such that it's equal to 0 or not equal to 0. Step 2 is the critical value, as always. In this case, again, it's going to be based on n minus k minus degrees of freedom. And the test statistic itself is nothing more than a ratio, as you can see here. Lastly, we're going to create a confidence interval and a prediction interval for your prediction y. And so there's two versions of this equation. There is a slight difference between each one. The first one you see here is the confidence interval for the mean value of y. Because x doesn't predict y consistently, accurately, there's going to be a range in which y is going to show up. So if x is 40, one time y could be 10, another time y could be 11 or 12 or 9 or somewhere around there. So if you're looking for the average of those numbers, the interval, the mean value of y, is going to look like this. You're going to have your estimate plus you're going to have some sort of margin of error. Alternatively, if you would like to make a prediction for a particular value of y, and this will be very clearly indicated on any exam for a particular y or specific y, the equation is still the same, except you add a 1 to it. This will make the range wider to account for the reduced accuracy. So this has been part 2 of the main points of chapter 13. I'll move on to a comprehensive problem that will address a lot of the points that we've seen together here.